Okay, we'll be going over homework 2, part A, where we are going to be defining or deriving our rectifying lines or our operating lines, one being the rectifying, stripping, and feed lines of our distillation column from mass balance expressions. So, in order to kind of get a baseline going, we're gonna and how these and what these will be used in. We'll go ahead and go over the McCabe-Thiele diagram right here. So, it's going to be our vapor composition on our y-axis and our liquid composition on our x-axis. And then this is going to be the compositions based off of our most volatile component in our distillation column. So the first line that is drawn for a McCabe-Thiele is going to be our 45-degree line, which is basically just saying that our liquid and our vapor compositions are equal to each other. So it's just x equals y line, 45-degree line. And then the next line is going to be our vapor liquid equilibrium line right here, which is basically going to be a theoretical line that depicts what our compositions are going to be for our most volatile component in according to certain compositions based off our vapor or our liquid phases. And it's kind of like just a theoretical line that tells us those numbers. So, and then the next line is going to be our rectifying line. And this is going to start off at our distillate compositions of our vapor and mole compositions. So we'll have our XD right here, and our YD, and then this will be modeled after our distillate, and we'll just kind of take a guess here first, and we'll say that it kind of goes like this. And then at the bottom, we're going to have another line. This is going to be called our stripping line, and it's going to start at our compositions of our vapor and liquid at the bottom. So we'll just say it starts about right here, and we have our X and B, and we have our Y, B. I'm going to these. Y, X. Okay, and the next line is going to be our Q line, which is going to start at our compositions of our feed at our vapor and liquid compositions. So we have we'll say that's, oh wait, hold on, forgot to draw the line. We'll take a guess here at our stripping line, and we'll say it crosses about there. Okay, and then we have our feed, which we'll say is about right here. So we have our XF and our, say, YF. And that's going to be about right here. And then this Q line, we'll kind of just make a line right to there. And this will be our Q line. Okay, and the next thing that we can do with this McCabe-Thiele diagram is figure out how many stages we are going to need in our distillation column. And to do that, we'll start at our rectifying line, and we'll go to our VLE curve, and then we'll go down to a rectifying line. So we'll start with that. So I'm going to redraw this VLE curve real quick, a little shallower. So we'll go here, and then we'll drop down to a rectifying line, and then we'll go here. And then once we cross this like intersection point, that's when we start switching to where our stripping line starts to be the driving factor here. So we'll switch to that line and go down to our stripping line, go here to our VLE curve, back to our stripping line, our VLE curve, back to our stripping line. Once we reach our desired bottom composition, that's where we'll stop. And then you can count these out. So we have 1 right here, and we have 2 right there, 3, and 4. So we're going, yeah, okay, yeah. So we're gonna have 4. According to this, we'll have 4. We'll have 4 levels that we're going to need, or stages that we're going to need for our distillation column. And we'll kind of draw this out real quick. So we have our 0 right here, which is going to be our condenser right here. And then this will be have a vapor in it, and it's going to have a liquid in it also. And our distillate will be coming out of the liquid. Okay, and then below that we'll have stage one, and draw a box for that too. And it's going to have a vapor and a liquid in equilibrium here, and we'll have our reflux coming in from our liquid reflux coming in from here. Should be L0, should be our reflux. And then we'll have our vapor coming up from our stage one. So this will be B1. And then we'll have our second stage right here. Which is be our, we'll have another equilibrium interface here. So V and L, and then draw another box for 3, D and L, and then our fourth one. And we'll have V and L. Okay, and out of each of these, we'll have a vapor going up from the bottom one up to the top one. So this will be our vapor from our second stage, and then we'll have a liquid coming down here from our first stage. And this will keep happening for every stage. So we'll have V3, L2, V4, L3, and then we'll have our bottom being pulled off, which is from where our stripping line is derived from, which is, I'll label that. So I'll have a stripping line right there from where our bottom composition is derived from. And a couple of assumptions that we have here are our vaporization is going to be equal for each vaporization that happens. They're all going to be equal. We're going to have 1 mole of liquid per 1 mole of, we're going to have 1 mole of liquid evaporate per 1 mole of liquid that is condensed. And our heat effects aren't going to matter. They're going to be negligible. So we'll keep those in mind going forward. And next, so I kind of want to go to these assumptions a little bit more in detail because they're going to help us kind of derive our operating lines a little bit better. So the first one again is going to be our HVAP is equal for each mole evaporated. And then 2 is going to be our, we're going to have 1 mole of liquid evaporated for every mole of vapor of our vapor condense. So our liquid condense is equal to vapor. Oh, I got that backwards. Liquid evap equals a vapor condense. So number 2 is going to be really important because as 1 mole of vapor is condensed and then 1 mole of liquid is evaporated, that's going to keep kind of how much of each phase we have in our distillation column is going to be equal. And once our stages reach a steady state, we're going to have a constant volume in every stage that we have, which is going to help us with our mass balance equations. And then 3, heat effects are negligible. Okay, so looking back on 2, our liquid evaporated equals our vapor condensed. We can use this to derive an equation for our rectifying line. So at the top here, we have our distillate and we have our V1 and L0. So our V1 and L0, the difference in that is going to be equal to our resulting distillate. So we can write that out. We have our V1 is equal to our L0, or not, minus our L0 is equal to our distillate. Okay, and so looking back at our number 2 assumption, since this results in having a constant or a steady state. This results in a steady state because of that. We can say this is true for each of the stages that we have up into our stripping line starts to be the driving factor. Also, I forgot to put the feed in here. So our feed is going to be, we'll put that at our 2 right here, and we'll just have our feed going in here. I forgot to put that. But back to our rectifying line, our V1 minus L0 equals D. So since we are in a steady state, that's going to be true for our V2 minus L1 equals 0. And our, and our V3 is equal to our V2 is minus our V3. Our V3 minus our L0 is equal to our distillate, so L2. So this will be helpful deriving our equation because we can then say that our V minus L altogether is equal to our distillate. So V minus L is equal to our distillate. And since our rectifying line is based off of our most volatile component, we want to get that in terms of that. So we'll use our V on and then Y. And then since our like we have L0 coming down here and V1 coming up here, they're different from each other. Like our V1 and L0s are different from what we need. Where if we just write Vy minus Lx equals Dx, it wouldn't be right because these two are coming from different stages. So in order to adjust for that, we do J plus 1 minus Lx equals Dx of 0. Okay, and we can then add the L over and then divide by V to get our vapor composition on the left-hand side by itself. So Y equals J plus 1 dx0 over is equal to dx0 dx0 over our V, and then plus our L over Vx, and then you should have a J here. So we're trying to do like a counter system. Okay, so we have this. So the next thing that we're going to do is we're going to substitute in our up here we have our V minus L, and we want to get our distillate involved and substitute it out for our V. So we'll solve for V here, and our V is going to be equal to L plus D. So we'll go ahead and substitute that in. We have Y, A plus 1 is equal to dx0 over L plus D plus our L over L plus dx J. Okay, and then so the next thing that that's gonna kind of model our rectifying line is going to be our reflux that we have here, our reflux ratio. That's going to be something that we have control over, and that we're going to want to model our operating lines off of. So this needs to be a part of our equation here. So R is going to be equal to our total liquid over our distillate coming out in our total liquid. And that's going to correlate to how much our ratio here of our liquid coming back into the system. So we can use this and plug it in here by dividing everything by D. So we have Y, J plus 1 equals D divided by D over L divided by D plus D divided by D x0 and plus L divided by D and then L divided by D again plus D divided by D xj. And then we can plug our LD for our LDs down here, and our D over D will be equal to 1. So we have Y equals J plus 1 equals 1 over r plus 1 x 0 plus r plus r, or divided by r plus 1 xj. And this resulting expression here will be our rectifying line. And this is only deemed possible because of for every liquid evaporated, every mole of liquid evaporated, we have 1 mole of vapor condensed. And we can use that here to model our finding equation for our distillate with our vapor and liquid involved. And we can substitute some things in here to get our rectifying line in terms of our reflux ratio. So the next thing that we'll do is we'll talk about how our compositions here are equal to our rectifying line and why that is. So the next thing that we'll show is that the rectifying line does indeed start at on the 45-degree line, which means that XD is equal to YD. So how we do this, we'll just say that our XJ is equal to our XD. So we can plug this into our equation right here. So we have YJ plus 1 is equal to 1 over R plus 1. And then we have our PD. We have our XD, and then plus R over R plus 1 XD. And then we can combine these right here since we have like terms. And YJ plus 1 is equal to R plus 1 over R plus 1 XD. And so this will cancel. And so we're left with Y equals J plus 1 equals XD. So we can see that our Y equals our X, which is our 45-degree line. And that is why our rectifying line will start on our 45-degree line. Next thing that we'll go over is the stripping line. Okay, so we'll be going over our stripping line here on our McCabe field diagram. This one starts at the bottom compositions or on our 45-degree line. So our liquid composition at the bottom is going to be equal to our vapor composition, and we'll prove that after we derive the equation for it. And deriving it is going to be pretty similar to our rectifying line. We'll have a vapor coming out, which is going to kind of go with our reflux. It's just going to be our reboil factor kind of rate thing that we'll use instead of the reflux rate ratio. So we'll use that in the derivation. And then our mass balance is going to be a little different. This time we have liquid coming in. So it's going to be our liquid minus our vapor is going to be equal to our boiler, or not our boiler, but our bottom outflux. So but we can just summarize this as L minus B equals B because of the assumptions that we made earlier about how this is our evaporation is equal to our condensation in terms of moles, and we can use that to assume that L minus B is equal to B. So we want to get this in terms of our composition for our most volatile component. So we'll do L equals XJ equals B YJ plus 1, and we're going to be using the same number like counting system that we used when we made our rectifying line because we have two different variables here. So and then we'll have our plus, well, I guess we need to solve for L up here. So L is equal to our V plus B. But we have our vapor composition for most volatile component, and then we want the bottom composition too as well. So B times our XB. Okay, and so we want to get Y isolated on the left-hand side. So that will end up being Y. And then we have J plus 1 is equal to our L over V, which is going to be L over V x j, and then minus our B over V x B. And we have a reboil right here, and that is going to be equal to our, so that's going to be equal to our, we'll call it V. V is L over our B, and that'll give us our ratio. And then we can do the same thing that we did for our rectifying line, is just divide everything by B. And one thing I forgot to say is when we're talking about the stripping line, we want to have a bar over our L and V, just to avoid confusion when we're talking about it. Okay, so and then everywhere we see an L over B, we'll replace it with our okay, so before we start replacing everything with our VB or our reboil ratio, we want to substitute in our L equals V plus B, because our reboiler is in terms of V over B. So we want J plus 1 equals V plus B over V x J minus B over V x B. And then we divide everything by B on the numerator and denominator. And every time there's a V over B, we replace it with a VB, with our reboiler ratio. So VB plus 1 over VB x J minus 1 over VB x B. And this will be our stripping line. So the next thing we need to do is we need to verify that the stripping line is going to start on the 45-degree line where y equals x. So we'll set xj equal to xb, and we'll go ahead and plug that in. And we'll have v plus 1 over vb xb minus xb over vb. And we'll have y j plus 1 equals our, we'll go ahead and distribute this out. So x VB plus XB minus XB. And then we can go ahead and combine these, and we can see that these will cancel out. These will cancel right here, and we're left with y equals j plus 1 equals xb. So right there, we can see that this ends up being y equals x. And that is the reason why it will start at on the 45-degree line. So that is how the stripping line is derived for the McCabe diagram, or graph. Okay, so the next thing we'll be going over is our Q line derivation. This is going to be a little more involved, because we're going to have more. We're going to be dealing with the rectifying line and the stripping line from where our feed comes in. So there's going to be more mass balances going on that we'll have to deal with and involve in our equation. So to start out, I'll just draw a little box right here about where our feed is coming into. So we have a feed, it's going to be F, and it's going to have a composition of Z. And then we're going to have our liquid coming down here. Our liquid, and this is going to be our L bar, because this is now going into our where our stripping line is the driving force here. And then we're going to have our vapor coming up, and vapor, and that's going to be V bar. Okay, so we need to write a balance about how much liquid and vapor is coming in from our feed here. So that's going to be our, and the way we do that is with a feed quality. It's basically like Q is basically going to be equal to a fraction, like a fraction of how much vapor or liquid is in a, it's how much liquid is in the feed. So if there's a 50-50 ratio going on, Q is going to equal 0.5. And then if there's a 1-0, if it's just straight liquid, it's going to be 1, and so forth. So we'll use Q in order to derive the overall or a mass balance for liquid coming in with the feed. So we have L is equal to L plus QF. And then for the vapor, it's pretty simple. We're just going to have V plus, and then it's going to be the 1 minus Q, because what isn't the liquid is just going to be the vapor times F. So that's going to be the balances for how much liquid and vapor is coming in with the feed. The next thing that we can do is we can go back and look at how we derived our mole balance for our distillation in our bottom feed. So it was L equals V plus B there. And then over here is going to be our V minus L dx. So we can go ahead and write those down. So we have Vy is equal to Lx plus dx0. And then we have our Lx equals Vy plus Bxb. And these again are just our mole balances for our most volatile, our mole balances for the composition of our most volatile component. So we can go ahead and add these together right here, since we need to take into account both, since both are involved with our where our feed is going into. So we'll add these together and we'll end up with Vy plus Lx. Hold on. This should have a bar. So Vy plus Lx is going to be equal to Lx plus V bar Y plus Bxb plus dx0. Okay. So now we can look at this right here, and we can realize we're going to write an overall mass balance for the whole distillation column. So the two things we have going out is the distillation, or the distilled, and the bottom, and then we have a feed coming in. So with a Z as our composition. So this is just going to be F Z is equal to our Bx B plus our dxd. Okay, so we can go ahead and substitute that. So we have Vy plus Lx equals Lx plus Vy plus Fz. And then we're going to group these terms together, our liquid terms and our vapor terms together. So we'll end up with Vy minus V bar Y, and then plus our Lx bar minus Lx. Okay, and so we can look over here and we can see that we can make a substitution. So this right here is just going to be equal to this right here, and this right here is just going to be equal to our QF. And then and this equals Fz. Okay, so we can go ahead and make our substitutions. So we'll have 1 minus Q here times our, well, and we have to carry over our y's here still, so the Fy and then plus QFX equals Fz, and then we can go ahead and divide both sides by F to cancel those terms out. So those will cancel out, and you're left with 1 minus Q, and then you have Y, and then plus QX, and then equal to Z. And so we're going to do what we did for the rest of them, is we're going to isolate our Y. And so we'll do that, and we'll have Y equals negative Q over 1 minus Q. And that's going to be X, and then that's going to be plus our Z 1 minus Q right there. Okay, so we have that, and we're going to go ahead and clean this up. So we have Q minus 1 instead of 1 minus Q, just to make it a little bit easier. So this is just going to be Q, and then Q minus 1, and then flip the sign here, and then I'll flip this around. So there's that, and this is our Q line. So that's our Q line right there. That's how we derive it, by using all the mass balances from our stripping line and our rectifying line with an overall mass balance of our distillation column. And we put those together and we derive our Q line right here. So the next thing that we need to do is we need to verify why our XF and YF are equal to each other, and therefore we'll end up on the 45-degree line. And we'll do how we did that with everything else. We'll set our oh, I forgot our X here. We'll set our X equal to Z right here, and we'll go ahead and solve. And at the end, our Y should equal Z. So Y is equal to Q over Q minus 1 X, and then minus X Q minus 1. So, yeah, all right. So we'll end up with, I'm gonna move this over here just to give myself more room. So we're gonna combine these two since we have a like denominator. So we have QX minus X over Q minus 1, and then we'll pull out the X, so we'll end up with Q minus 1 X over Q minus 1, which is equal to Y. That was cancel. We end up with Y equals X. And that is how it ends up on the 45-degree line. So yeah, and that's that. So we have our Q line, we have our stripping line, and we have our rectifying line here. And we saw that if we made our XJ equal to our XD, that they would end up, that Y would end up equal to our X composition. So, and that's how they all three would start on the 45-degree line.